Hello and welcome to AI4. Our next session will be led by HUYEN. She is the machine learning engineer and open source lead at Snorkel AI. Please join me in welcoming Chip to the virtual stage.
Hello, thanks Pachika for the introduction. My name is HUYEN and I'm super excited to be here today. So let me just share my slide really quick. So today I will be talking about machine learning in research and machine learning in production, the gap between them and how we can bridge the gap. So to start, I just want to introduce a little bit about myself, my background. So I come from the least techie background. Before, so I had been working for a long time as a writer. I actually published 4 books, and I also work a little bit as a product manager and creative director. So I have launched Coco browser, Vietnam's second most popular browser with more than 20 million monthly active users. So I started doing machine learning and AI when I got to Stanford, where I did my bachelor and master's degree. I also created and taught during my time at Stanford, I created and taught the course TensorFlow Deep Learning Research. I did machine learning research at Primer, Netflix. I did applied research at NVIDIA, and currently I'm focusing on machine learning in production at Snorkel. So I'm just gonna do a quick 1-minute introduction about Snorkel. So Snorkel AI was spun out of Stanford AI Lab. Our core algorithm allows users to use heuristics to programmatically instead of manually label data and create massive data sets. And we also built an end-to-end platform on top of the core algorithm. With it, users can develop and deploy AI applications within hours, not months. I'm also like a bit nervous, so I might speak with a lot of minor, and I really hope that you forgive me for that. So for my talk today, my talk today consists of 5 parts. First, I will go over the difference between research and production. Second, I will cover the 3 main stages in a machine learning production pipeline, like data pipeline, modeling and training, serving. And then for a few minutes at the end, I will just take a look at the landscape. So for first, is the difference between research and productions. From my experience teaching and hiring for machine learning engineer roles, I realized that a lot of people who came from academic backgrounds, for example, they have taken machine learning courses in college or online courses. They usually have a shock when they have to encounter machine learning production because it's very different from what they're used to. So the first difference is in the performance requirement. In research, in the research community, there's currently an obsession with state of the art. So people want a paper that beat current state of the art, like to get on top of the leaderboard. Whereas in productions, if a simple model can get 90% of the work done, and state-of-the-art models are very complex, can get 96% of the job done, you might want to go with the simpler models because it's easier to deploy, less error-prone, and easier to interpret. The second is a priority. So training is when you train the model, and inferencing is when you use that model to make predictions on unseen data. So in research, you have to do training multiple times. You have to train multiple versions. So you want training to be fast, and you only have to run inference a few times to report the result for the leaderboard, or to compare with other existing models. Whereas in productions, you train the model, and then you have to use that model on just to serve the users. So you have to run inference millions, if not billions of times. Another is in the difference in the data. In research, data is static by design, so that different teams, research teams, can benchmark on the data and compare the progress. Whereas in productions, the data can constantly shifting. For example, you might run a new marketing campaign, and suddenly you get a lot of users from a demographics that you've never had before, which totally change the distribution of the data. Another is fairness. We they say like sadly in research still good to have. So in research, because our research is not yet used on users, a lot of researchers tend to put it off as an afterthought, thinking like, oh, I will worry about like fairness when it gets to productions. But usually when it gets to production, it's already too late. We have seen a lot of backlash or sad stories on how machine learning algorithms can discriminate against humans, against users. So I think I read recently on a book I like. It's called A Weapon of Math Destructions. It says that like machine learning algorithms don't predict the future. It's only encode the past with all the biases that humans have. So but if a person can also make sweeping judgment and discriminate against one person at a time, algorithms can discriminate against people at scale, and it's a very dangerous thing. I also want to talk about interpretability. So nowadays, most of us are happy to use microwaves. We don't understand how it works. But sadly, we are still not that ready to use machine learning or AI algorithms without wanting to understand how it works. So for example, like if a users applies for a mortgage for their dream home and the application gets rejected, the users interpretability is important, not only because the users deserve to know why, but also like being able to understand how and why the model makes decisions can help us avoid the biases that mentioned above. So I think Geoffrey Hinton, one of the godfather of AI, which we sometimes jokingly refer as the holy tea of AI, of deep learning, he posted these questions on Twitter. So if you have an AI surgeon who has a 90% cure rate, and but can't explain how the algorithm works, and a human surgeon who gets an accuracy of 80%. So which one would you go with? And when I once gave this talk to a group of technology executives at like public company, and about like 50% of them chose the AI surgeon, and the other chose the human surgeon. So I guess we still have a very long way to go with accepting AI as a black box. And I think even covers this partly during modeling, as in, so during research modeling, it's a hard part, whereas in production is everything else. So the next I will talk about the machine learning production pipeline. In school, like in courses, when we did some test project, we might think of it as a very linear path. Like you have the project set up, you get the data, you train the model, and then you serve. But actually in productions is a lot more complicated. So for example, you might train the model, and then when you look at a test score, and you realize that a lot of the low performance is not because of the model, but because of the noisy label, bad label. So you have to go back and relabel the data. Or after you serve the model to users, you realize that the assumptions you have made during training the model no longer apply to real world users. So you need to like go back and maybe like reformulate the problem. So data pipeline is the first. So because project setup is usually, I will not cover project setup in this part because it's more project management skills than machine learning. So I will go straight to data pipeline. So I guess I don't have to preach this audience the importance of data. So deep learning, the progress of deep learning in the last decade have been driven by data, and the best products are usually not the companies with like extremely clever algorithms, but usually like by companies with the best data. And for data, I also noticed that like for data we have sort of public data and proprietary proprietary. I can't say that word. I'm too nervous to say, so I'm gonna skip it. So I think this slide by Andrej Karpathy from Tesla pretty much embodies the difficulty of data in productions compared to data and research, or during his PhD. And also like it's a pretty great talk if you want to look it up. So for data challenges, in research, so the data is so clean. I miss a day when I can just like get the data of some workshop and then work on it. But now in production, the data is like so noisy and like it might be so large. Like it has so many fields, so many features. You don't really know like where to start looking. It has like a lot of missing values in all the random places. It has missing labels. If you have labels, it's very noisy. It's constantly changing. It has like unknown quirks that you like you just don't know. Like sometimes there's some maybe encode a number is strange or what it should be string is now a number. It's very complicated. And for there's a lot of questions you need to ask yourself during the data pipeline for the project. And here's just some of them. Like you have to look into the data availability and how you collect and store the data. If you have to work with user data, what concerns you have to think about. Data preprocessing and representations. And don't even get me started on data versioning because it's really hard and I haven't seen anyone doing it really well. So I also want to talk a little bit about on the ethical concerns when we work with data. I think there have been a lot of discussions on this topic recently, and I think it's a great direction to do. But I think there's still so much work left to be done. Like there's so many problems we're not yet even aware of. Or like we're aware of them, we don't really know how to address them. For example, the problem like with data ownership, right? So so if someone train a model and make money out of the data, then who is gonna make money out of it when you get anything? I also has this like recently has a very chilling experience. I was looking at just like a data set online, and then I found there's a lot of tweets. And then I look it up and I saw that there's a tweet by me. Like I already deleted it on my Twitter, but now it's still in the data set and there was no way I could delete it or had any control over it. So like people say the data is anonymized, but then like, is it possible to, after serving the model, like people can reverse engineer and take a look at the data it was trained on? So there are so many questions. So we can move to the next part, which is less headachy and maybe a little bit more fun, is modeling and training. So this is a part that is usually taught in most machine learning courses, how to build a model and how to train it. So this is often the easier part of the machine learning production pipeline. And I'm not saying that building, developing a model is easy. The fact actually like to create new architectures that can perform well is very, very difficult and expensive endeavor. But luckily, a lot of the models are being commoditized, which means that most companies will just use off-the-shelf models instead of developing their own. So that's why I'm saying modeling and training is the easier part. So I have this process of have this experience a lot when working with clients. So I see that many clients, many companies like to follow buzzwords. For example, like whenever a new model is come out, they would come to us and say like, oh my God, we just heard about this word is amazing, or this GPT is really amazing. Can we use this in production? And maybe like, actually you don't need BERT, you don't need GPT. I think for the problem, a simple logistic regression is good enough. Like might is a trick, but they were like, but we want to use state of the art. So usually we still have to give it to them so that they can try it out for themselves and realize that a similar model is better. So when we work with clients, when we develop the solutions, we try to tell them that be solution oriented, not technique oriented, and don't follow passwords. During the process of developing models, I also see that a lot of engineers tend to overlook baselines. So many, so they can just build a model and say, oh, my model is like 98% accuracy is good enough. But metrics by themselves don't mean anything. Like you can say a model with 98% accuracy, but if the data set, like if the label attribution is skewed, and you can just make like some prediction by, for example, like if you work with the task of like predicting whether somebody have a rare disease. So like 99.99% of people will not have it. So if you can just predict like on the samples as they not have the disease, it will have the 99.99% accuracy. So the metric is themselves don't mean anything, and you have to compare them to like various baselines. For one baseline is like easier, like it's very straightforward. It's a random baseline. Like if the if you just predict the output as a random, how good the model, what is a score you're gonna get, or you can have this with human base like if a human expert does this task, what is how good will the result be? So that's why you can say that whether the algorithm is below the human performance or like superhuman performance. Then so Oracle, if it just trains or if you can just like train the model on train set and test it on the train set, what score would you get? And also like the next baseline I want to talk about is simple heuristics. A lot of people underestimate like good heuristics. So I would so first of all, you can think about the task of predicting what app users could use next on the smartphone. And so a simple heuristic would be like just to show them like the most used apps, for example, like I don't know, Facebook Messenger or WhatsApp. And usually like it might get you like 70% accuracy already. So if a simple heuristics can do the trick, then a more complicated models have to have like much better performance to justify the added complexity. So I really like this quote by Martin Zikovic from Google. He also has this very nice booklet, A Machine Learning Engineer, if you want to look it up. So he said like if you think that machine learning will give you 100% boost, then a heuristic will get you 50% of the way there. Also like a silly part is that like a Snorkel, we allow you to incorporate heuristic in building the model. And it's pretty straightforward for you to use heuristic or like share domain expertise across the organization. During the process of developing the models, you can encounter a couple of catch-22. So one is a developing catch-22. Like you would need data to develop a model because the building algorithms need data, but then you can't collect data, user data, without only having a model. Another catch-22 is just for a lot of companies, they want to test like different developing potential without like throwing too much money into it. But then like for deep learning, because you need so much data, you will need to like invest upfront a lot of money into data labeling and training models to see good performance. So there's solutions like how can we just like try out some deep learning algorithms without a lot of investment upfront in data labeling. So one solution called like moonshot is like, how about we just like use algorithms, like answer algorithms that don't need data labeling. I haven't seen it like being used successful in production yet. So, but if you guys have some lead, we'd be happy to hear. Another that have been certain success, like actually what we do a Snorkel AI, is weekly supervised, which is you start with a very small label data. It can be like, or it really depends on the task, but it can be the order of like hundreds of samples. But like, don't quote me on this, really depends on the task. And my boss may be very unhappy if just like throw out a number like that. But then based on that, you can like label a much larger data set. So, and of course, if you work with code, you will have to debug. And I think at some point I made a joke on Twitter, and I think that was a peak of my career for the attention I got from it. So they have been like, debugging for machine learning is so hard that there have been like a lot of people making fun of it. So why is it so hard? The first is that because machine learning is still a black box. You can't really debug a program if you don't understand it. The second problem is like you have a lot of invisible bugs. Like the model can compile and the loss can go down, but actually not learning anything. Or there's so many factors that can cause a model to perform poorly. And here I'm missing out 5 factors, but there are like many more. First of all, one reason why a model performs poorly is like because of theoretical constraint. It's just like poor model data fit, because these models make certain assumptions that the data doesn't have. So it's just like if you throw the model onto the data, it's just not gonna work, no matter how good the implementation is. The second is just like poor implementations. Or like sloppy training techniques. I'm not sure if you use PyTorch, you probably have seen this a lot, like just forget to call like zero grad or like code train instead like model eval, and it can be painful. So poor choice hyperparameters. So I have seen this a lot. Like one set of hyperparameter can give you like really, really good performance, whereas another random seed can just like another set of hyperparameters just doesn't converge at all. So like if you choose poor, yeah. So you might think, so when you see a model perform poorly, it might be because the model is bad, but it can just be because like you just need to switch up the hyperparameters. And so there are a lot of data problems, mismatch input labels, like over pre-processed data or noisy labels, and you have to investigate to figure out what you want. So and also like during training, scaling has become more and more crucial. So giving rise to like demand for engineers who can deal with very large infrastructure. So as model become bigger, so we have like model, so we have problem of like the model can't fit in memory because we use more data can't fit in memory, and like we use more GPUs, very large batch size, like batch size. So if you guys have read literature recently, like GPT-3 actually uses the batch size like 3.2 million, which is like unheard of. It's a massive engineering challenge. I have so much respect for OpenAI engineering team to pull that off. For the next part is surveying. So after you train the model, like how do you serve it to users? How do you deploy it on a do you want to deploy on a server and people can send requests there? I want to deploy it on the user devices like their phones or other edge devices. So large models. So during surfing, one problem arises is model compressions. Large models are slow and very costly for real-time inference. Then how can we compress model? Like first to fit into like the user device, and second, like we're hoping that like if smaller models can do inference faster. I haven't seen a lot of startups doing this yet. So there was one startup that was in Seattle, and they raised like $60 million, and they got immediately acquired by Apple for like $200 million. So it's a very exciting area to get into right now. Also, like there's a CICD test. So like every time users make a change, every time a developer make a change or code piece, you want to run the test, you make sure that nothing got broken. But because machine learning tests take a long time to run, it might really slow down the development cycle. And also monitoring and analysis. We talk about like how the data can change constantly. So how do we monitor our deployed model to know that when it needs to be updated, or even needs to be updated, then how do we do it? So quickly, I think I ran out of time here. So it's like want to go over the landscape. So I looked up like 200 machine learning tools that I found to help people develop machine learning models. And here's like 200 actually the own what I can found, which means that the space is actually very underdeveloped. And you can see here as you can see the data pipeline pretty much develops the dominates the landscape. But recently we have seen more interest in surveying, and it's a very exciting process. I also broke down like plotted on the tools based on the main problems they address. And you can see that a lot of the tools are framework and data management, labeling, database query, data processing, and very little on this as in CI/CD, AI as a service, or hardware compatibility. And if you're interested, I actually wrote about it on my blog. Feel free to check it out. And thank you very much for your attention. If you have any questions, please reach out to my email. Is my personal email, or if my Snorkel email is at the beginning of the slide. Thank you. Bye-bye.
Thank you so much, Chip, for that incredible presentation. A huge virtual round of applause. Yay! All right, if you're looking for your next session, you can go ahead and check out the program page or take some time to connect with your peers with virtual networking. All right, thank you again, and we'll see you around.